Hello, it's Bronson here from Professor Okamoto's afternoon class. Today I'll be talking more in depth about offshore wind turbines. Brief introduction to history. The first offshore wind turbine was installed off the coast of Denmark and Vendeby in 1991. Most of the projects are built in Europe, with an accumulation of approximately 4,000 wind turbines built, also representing about 90% of the world's total. However, the UK built the most out of the European countries, consisting of half the total power generation, with its largest farm, the London Array. It is also heard that Ørsted's Hornsea Project 1 will make the London Array hold the world's largest turbine, the Haliade-X, with its completion in 2020. In contrast, the US has only started building commercial wind turbines, with the first project in Rhode Island finished at the end of 2016, which consists of 5 turbines with 30 megawatts of capacity. Why did I choose wind turbines? Offshore wind turbines just interest me, especially with how large-scale each building project is. Nevertheless, this topic can be seen in a much more modern view, especially since offshore wind farms have only recently been operated since the 1990s. Unlike its counterparts on land, the projects offshore definitely proved to be much more laborious and technologically innovative. First off, we take a look at the basis of the construction of offshore wind turbines. Contrasted from the ones on land, the ones offshore requires much heavier construction due to its larger scale and range. The wind turbine has its blades and hub attached to the nacelle resting on top of the tower that leads down to the transition piece. The nacelle of a typical 150-meter tall wind turbine, one that can generate approximately 6 megawatts, is about 600 tons in weight, while the blades are 27 tons each. Typically, the rotor diameter is compared to approximately 1 to 1.2 times the length of the top of the tower to the transition piece. The transition piece remains at the bottom of the base of the turbine, which then connects to the monopole, a steel tube drilled into the seabed, attached to tripods that secures the tower onto the seabed. The transition piece allows for the connected cables to transfer the wind power generated to a large-scale grid on land. This electricity is channeled through coastal load centers that prioritize where the electricity should go and distributes it into the electrical grid to power our homes, schools, and businesses. Wind companies has recently started making floating wind turbines, 3 kinds being the ones depicted on the picture: the spar buoy, semi-submersible, and tension leg platform respectively, each with their own levels of base underwater reinforcement. As we can see, semi-submersible has 3 pillars acting as connecting entities at the surface of the water, which can prove more stable than relying on the main tower itself. Branching off of that matters on base design. The wind turbine design requires it to be at suitable locations. There should be suitable water depth, suitable seafloor geology, won't clash with other sea functions and stakeholders such as fisheries, oil and gas platforms, contain subsea pipings and cables, requires sand extraction activities in their respective shore, also have environmental factors such as avoiding any vicinities that protect nature areas and bird migration routes. Finally, avoiding any possible radar interference from nearby military bases. The size of the wind turbines offshore is comparatively much higher than the ones onshore, obviously due to the geographic disparities and the fact that much of the areas offshore has a greater level of wind blowing in. The 6 megawatt capacity Haliade turbines that the US has built had a rotor diameter of 150 meters, and that is usually the range that the rotor length falls into, around 130 to 180 meters. The Adron 8180 from Spain has a rotor length of 180 meters with an 8 megawatt capacity. Typically, the longer the rotor diameter, the higher the potential power generation. However, the world's largest MHI Vestas, which used to only have a capacity of 8 megawatts and now upgraded to 9.5, is only 164 meters in rotor diameter length. Nevertheless, the upcoming new Haliade-X design has a potential 12 megawatt capacity, along with a colossal 220 meters rotor length. Let's get started on the interior design of the turbine nacelle. The nacelle of an offshore turbine is essentially the same as onshore ones, except of course, its scaling. The length of the nacelle is approximately 15 to 20 meters long, and as we learned, the main components of its interior consist of the pitch controller for rotor speed control, an anemometer to detect the wind speed, generator and gearbox to produce electricity, blade joint to connect the blades, rotor for the blades and hub, yaw drive to make sure that the rotor faces the wind, and electrical circuitry to transfer the energy. Cost is a major issue for the construction of wind turbines, as a 150 megawatt wind farm offshore usually requires $1.2 to $2 billion to make, averaging around 60 to 100 million per turbine. Another hefty comparison between offshore and onshore turbines is that offshore wind power is estimated to cost around 22.15 cents per kilowatt hour of energy generation, while onshore wind turbines is about 8.66 kilowatts per hour. Steel is used to construct the tower and its lower components, while the main material to use to construct the blade is carbon fiber, with some implementing a mix of glass fiber and shells to wrap around the edges of the blade for extra adaptive protection. Offshore, the parts required are larger and in more sizable chunks. Therefore, lift boats are required to transport materials in order to build the turbines by sinking legs onto the seafloor, then raise a boat out of the water in order to create a balanced platform on which large cranes can operate and build a turbine. Yes, cost is a major detrimental factor in the construction of offshore turbines. The cumulative capacity of approximately 4,000 offshore turbines is 16 gigawatts globally, which was predicted to reach 25 by 2020, and that requires an immense level of materials and costs. However, the payoff of energy generation is substantial. This can especially be observed at the US since the energy consumption in the nation is higher near the coastal areas such as California, and wind speed is also much higher than the ones onshore. Here are my sources. Thanks for taking the time to watch my video.